Hi. So, in this class thus far, we have used graphs to kind of describe a lot of different phenomena. We've used it to describe displacement, velocity, and acceleration. All of these concepts are nested within each other. Thus, it's important for us to be able to interpret a graph. Now, when we look at a graph, we typically look at an xy axis. So, just to go off with simple things, start simple and build big, we have our x-axis and our y-axis. We know that our x-axis equals our independent variable. We know that x-axis independent. And we know that our y-axis is going to be our dependent variable. If you're not familiar with these terms, to cover them, the independent variable is a variable that's going to happen no matter what you do. For example, time is generally the independent variable, because time happens no matter what. So, we know that generally, I'm going to just put t, because for the purpose of the graphs you're going to be looking at, it's going to be with respect to time. Then, we know our, I put that as our dependent. Oh. See, I still make mistakes, even at home. But we have our independent variable, which is t. Then we have our dependent variable, meaning it's going to depend on the time. It's going to depend on the independent variable. For example, if I walk to my neighbor's mailbox, which I can see out my window right now, it's maybe from here about 200 meters away. If I was to walk over there, my displacement would be 200 meters. But my velocity would be the time it takes me to cover that distance. Now, with this, we know that our dependent variable is generally going to be our delta x, our v, or our acceleration. So our displacement, our velocity, or our acceleration. So we already kind of have an idea. And the rest kind of just remains on knowing, how slope influences this. So slope equals y over x, or as many math teachers will say, they'll say the rise over run. Now, this slope has actually a unique implication. For example, if I was to make my x-axis time, and I'm just going to leave it as t right now, and I'm going to make my y-axis delta x. Now, if we know that slope is rise over run, so if I write this as it's consistently increasing, my displacement consistently increases with time, and we'll say at, 5 seconds, this object has traveled 20 meters. So we have delta x in meters and time in seconds. We get a very interesting kind of phenomena here, because if we know that at 5 seconds our x, our x-axis, our time, 5 seconds, and our displacement equals 20 meters, we can then conclusively say that if this, supposing this is, linear, supposing it's perfectly linear, we could say that our velocity equals our delta x over our delta t, our rise, our y-axis divided by our run. So we can say 20 meters over 5 seconds. We could say that for every second they're traveling at 4 meters per second. And that's how we work to interpret graphs within this field. We kind of, it seems scarier than what it is, but once you realize what you're looking at, it's actually not that bad. Now, I'm going to make another video so that way, we can kind of look at these in bite sizes. But this is just a general introduction on graphs, and I'll go more into the displacement, velocity, and acceleration.